Let's explore the CAP theorem. It's all about consistency, availability, and partition tolerance. These three concepts are key when designing distributed systems. The CAP theorem states that a distributed data store can only provide 2 out of 3 of the following guarantees simultaneously. First, consistency, where every read receives the most recent write or an error. Second, availability, where every request receives a non-error response, without guaranteeing it contains the most recent data. And third, partition tolerance, where the system continues to operate despite network partitions or communication breakdowns. Remember, you can only pick 2 out of these 3 according to the CAP theorem. This was proposed by Eric Brewer in the year 2000. Let's dive into consistency. Consistency means that all nodes in the system see the same data at the same time. When data is written to any node, it must be replicated to all other nodes before the write is considered successful. Reads will always return the most recently written value. The pros of consistency include data integrity, predictable behavior, and simpler application logic. However, the cons include higher latency for write operations and potential unavailability during network partitions. For a real-world example, banking systems prioritize consistency to ensure account balances are accurate across all nodes, preventing issues like double spending. Now let's discuss availability. Availability means that every request to a non-failing node receives a response, without the guarantee that it contains the most recent data. The system remains operational and responsive, even when some nodes are down. No request should ever be dropped or time out as long as at least one server is functioning. The pros of availability include high uptime, a responsive system, and better user experience. The cons include it may return stale data and eventual consistency challenges. For a real-world example, social media platforms prioritize availability to ensure users can always access the service, even if they occasionally see slightly outdated content. Let's explore partition tolerance. Partition tolerance means that the system continues to operate despite network partitions or communication breakdowns between nodes. When connections between nodes fail, the system still functions, though possibly with reduced capabilities. In distributed systems, network partitions are inevitable. Modern distributed systems must be partition tolerant. The real choice is between consistency and availability when partitions occur. In practice, the CAP theorem is often simplified to choose between consistency and availability during a network partition. Let's talk about CAP theorem trade-offs. First, we have consistency plus availability. In this case, all nodes see the same data at the same time, and every request receives a response. This works in a single node system or when network partitions are impossible. Note that this is not achievable in distributed systems where partitions can occur. Examples include traditional relational databases, or single node and two-phase commit protocols. Second, we have consistency plus partition tolerance. In this case, the system remains consistent even during network partitions, but some nodes may be unavailable. When a partition occurs, the system blocks operations to prevent inconsistency. It prioritizes data correctness over availability. Examples include MongoDB with majority write concern, HBase, and Zookeeper. Let's explore availability plus partition tolerance systems. These systems continue to function even when network partitions occur. All nodes remain available but may return different or inconsistent data. They use eventual consistency model. Nodes will eventually sync when partition is resolved. They prioritize system uptime and responsiveness over data consistency. You would choose these systems when availability is more critical than immediate consistency, and the application can tolerate temporary inconsistencies. Examples include Cassandra, which is a highly available NoSQL database with tunable consistency, DynamoDB, which is Amazon's highly available key-value store, CouchDB, which is a document database with multi-master replication, social media, for user posts, comments, and likes, content delivery, for media streaming and news feeds. Let's consider some practical considerations for the CAP theorem. CAP is often misunderstood as a binary choice, but real systems exist on a spectrum. Modern distributed systems often implement tunable consistency levels. Different parts of an application may have different CAP requirements. Network partitions are rare events, so systems can optimize for normal operation. The CAP theorem applies specifically during network partitions. When the network is healthy, you can have both consistency and availability. Consistency exists on a spectrum rather than as an absolute. From strongest to weakest: strong consistency, sequential consistency, causal consistency, and eventual consistency. In conclusion, the CAP theorem provides a framework for understanding fundamental trade-offs in distributed systems design. In practice, the choice is not about abandoning a property entirely, but about making strategic compromises when network partitions occur. It's important to understand your application's specific requirements before making CAP trade-offs. Different components of your system may require different CAP priorities. Consider the spectrum of consistency models rather than binary choices. Measure the actual impact of your CAP choices on user experience and system performance. The right CAP trade-off depends on your specific use case, data characteristics, and business requirements. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.